seminar for today. We've had some technical difficulties in the room. The projector isn't working.
Sorry.
So we're trying this through the side monitors, and hopefully, you guys are young, so we've got sharp eyes, and you're going to be able to see what's going on out there. Yes? All right? If you can't, you'll just have to come sit down in the front, I guess. Nobody wants to move up. All right. Okay, so today, exciting day. We have with us Ray Hogan. Where's my little cheat sheet? Okay. All right, we have Ray Hogan. He's from UT Texas at Texarkana. A very new program over there. They just started a chemistry program over there. So he wants to come to Laterno to see how it's done right. Yes?
Yes, sir.
All right. So he's probably going to be asking you guys a lot of questions about, the great chemistry program here at Laterno and how they get emulated over there at Texarkana. Right? But let me tell you a little bit about him. He's very local. He's a very southern sort of guy. He got his BS in chemistry from the University of Louisiana in Lafayette. Yes. And he did a few things, and then he ended up getting a PhD in inorganic chemistry at the University of Missouri in St. Louis. So, is it across the Mason-Dixon line in Missouri, or what? Close. Yeah. Close. All right. And now he's back at the University of Texas, starting the chemistry program there in Texarkana. And he's going to talk to us today about small molecule remediation using hydrogen bonded metal organic frameworks. Wow, that's a mouthful, isn't it? Yes? Can you say that fast 3 times? Try? No. Okay. All right, I want to remind you that after the talk, Dr. Hogan will be going to lunch with us. And if you want to join us in the Joyce room, ask him more questions about his life as a scientist and things like that, you're welcome to join us, and we'll see you over there. All right, let's give Dr. Hogan a
Thank you very much. It's a pleasure to be here. Appreciate the invitation, Gary. Just a fantastic driving through. The funny thing is we actually met on Tuesday. We were both down in Houston at the Welsh Foundation conference. So I actually got to meet Gary just a little bit in advance. So just like he said, I'm coming from Texas A&M, University of Texarkana. We actually just started our chemistry program. This is our 3rd semester, so the 2nd fall semester that we actually have a chemistry program thriving in Northeast Texas. So, I know you guys have one here, but very far Northeast Texas. All right, so, and my extra little pinpoint, I saw some of you with the athletics gear. Just wanted to let you know, the misnomer about athletics, and you can't be in science, right? Usually they always say if you're an athlete, you can't do all the science. I pitched 2 years at Louisiana Lafayette, so Division I baseball. So you can do it, okay? Just have to work hard. All right, so that's going to be my mindset, because one of the things, I keep striving as much as I can to be the best I can, best person, best scientist, best father, because I left my nice small kids at home to make this nice drive up here, or sorry, down here. Okay, so like the talk, we're going to look at what's called small molecule remediation using hydrogen bonded metal organic frameworks. This kind of field has opened up recently, more so I would say, probably within like a good past 20, 30 years, this idea of what's called a supramolecular chemistry, right? Because if everybody's probably a sophomore, juniorish, probably in this room, you guys have all taken organic chemistry, done fairly well in it, right? Everybody knows their SN2E1 mechanisms down cold, right? Backside attack, inversion of symmetry. Okay, well, supramolecular synthesis or supramolecular chemistry is actually not as well known, right? Like you see up here, we mentioned, if I get the laser pointer, yeah, it's all right. You can see at the top supramolecular synthesis. We all know it. You can take it from our basic organic textbook, part 1, part 2. any type of reaction, if we know there's something we want to make, there's a reaction scheme for us. We can go find it in literature or from our textbook and reproduce it at a very good high yield. Same thing on the inorganic, just a classic inorganic system. That you can do a basic kind of an oxidative addition across an iridium center where you can take a 16 electron metal center and add hydrogen across in kind of this little cis effect that you can generate the 18 electron iridium-3 compound. Okay, all fairly known or widely known. But the new one, maybe you haven't seen, but it's not a real classic type of chemistry. Supramolecular synthesis is probably, give or take, I know I teach this little portion in my Gen Chem Part 2 at the very beginning. So if you remember your general chemistry days, you got to that chapter about weak interactions, the van der Waals, remember all that? Not as widely known, probably covered maybe 20 minutes at the most on it. Talking about dipole-dipole, hydrogen bonding. Sounds familiar? Well, that's what supramolecular chemistry is. Okay, so in supramolecular synthesis, well, we have a wide variety, just like in organic chemistry, inorganic chemistry, there's a lot of reactions, but we are going to allow onto interactions to use for our advantage. So some of the commonly known ones, and you can see a rough energy associated with them, from as high as the ion, so that's a basic inorganic system since I am an inorganic chemist by trade. So we're just talking about metal, non-metal, cation, anion, and goes as far down as you can see the ion dipole, dipole-dipole, more especially in my case, the hydrogen bonding system. Okay. Now, what we are going to do in the supramolecular realm is we allow for non-covalent interactions to take effect. One of the biggest ones that actually got the topic of supramolecular chemistry into effect was actually a Nobel Prize won, I forget the exact year, by Peterson Cram and Jean-Marie Lehn, who started this idea of supramolecular chemistry back in the 80s. Right, one of their first systems was looking at this molecule, in this case just a basic 18 crown 6 ether, and where they actually put a potassium ion inside of the crown ether. So what is the interaction going on? There's no classic anion that's present. There's all the lone pairs of electrons associated with the oxygens that are pointed into the middle of this crown ether, and we have what's called an ion-dipole interaction. The dipole that's generated from the electronegative oxygen pointing into the center of the actual crown ether, and there's, lo and behold, the ion from potassium. Okay, it's not your classic covalent interaction. It's not a classic coordinate covalent from inorganic system. It's just this weaker interaction. All right, and then what I'm going to focus on mostly, that you'll see a lot of, that will beat the dead horse into the ground, is hydrogen bonding. All right, so simply where we can just take kind of components together and allow them just to interact, generating hydrogen bonding like you can see with a basic dimerization of benzoic acid, where we have a hydrogen bond acceptor and a hydrogen bonding donor who come together, who come together and form this hydrogen bonding interaction that you can see with the dotted lines in between the carboxylic acid group. All right, so in the grand scheme of things, what we're trying to make was, again, on the supramolecular system, what's called a host-guest system, right? Just commonly what you would think of, right? You have a visitor that comes to your home, right? They're the guest, right? You have the home or your apartment, wherever you may be. You're hosting that person. So our molecules are going to actually work in the same fashion that we will build frameworks that are going to be classified as the host, and we can put other little bitty molecules and say, like a remediation system, put molecules inside of these frameworks as guests. So as you can see, two different kind of areas of frameworks. To the left, you see a basic organic system. This is pure organic chemistry with the sense of supramolecular synthesis, because it's all organic molecules that have combined to form a hydrogen-bonded species. And you can see inside of the little framework, there is a paraxylene molecule just waiting right inside. To the right, a basic coordination polymer. So as you can see, a repeating unit of metal center, followed by some little bridge of a terephthalate acid, in this case a terephthalate, that's bridged between the two iron centers, giving a continuous extended array, what is called a coordination polymer. And again, inside, right in the little grid, you can see we have two molecules of DMF. Right? Nice little solvent, just fits right in. Okay, so what we're trying to show is we can have a variety of these host molecules that can be organic, they can be pure inorganic, or a combination, a hybrid system that I will show you later on as part of my research. Because if you remember from the title, it's called a metal organic framework. So we're actually going to combine the best of the two worlds. Okay, so all of these frameworks, especially what I'm going to be looking into, have one key common feature. They're layered. Okay, so one of the basic layered systems that you can think of is the basic silicates, clays. Right? Hopefully everybody knows the functionality of a clay. Right? You've probably seen it in the yard, especially give or take around this time, maybe a little earlier in the summer, right? You get those very large rainstorms. Your ground soaks up all the rain, it goes away, right? And you get a 3 week of dry heat. And what happens to the ground? It kind of cracks, right? You get all these big old cracks into your ground. Okay, well, what's happening is inside your ground you have clays. So as the water comes in, the clays will expand, water will go inside of it. As the heat comes, right, we know water will pretty much boil off, evaporate at 100 degrees Celsius when we heat it, get enough difference in pressure difference, water molecules will come right out. So once the clay has swelled and expanded to a certain distance and water comes out, well, it can collapse. Hence why you see all the cracking. Okay, so within a basic clay, what we are looking at is that ability to swell, the ability that the layers can move. Because if our layers can move and shift in their position, this allows for other guest molecules to come inside via this small molecule remediation. Okay, so again, just kind of showing you pretty much all the grand scheme of things that can happen. Right, 4 different types of layered systems. So now we're looking at the comparison of, again, another coordination polymer. I had to put this one on this slide because when I first started into looking at layered substances, it's kind of like in essence, one of my scientific idols onto the right-hand side, the left-hand side. This is from Abe Clearfield, prestigious professor emeritus over at Texas A&M, College Station, discovered one of these first coordination polymers based on a kind of has like a, as you can see, the biphenyl system that's in between, again, of a coordination polymer. And the picture to the right, again, a nice, you may be able to see it, may or may not, right in between all of these different types of molecules, the dotted lines, hydrogen bonds. So that is some lesser known guy by the name of Dr. Hogan. Well, that's me. So just trying to show you the comparison between the two, okay, that I have a layered solid as well, held together by hydrogen bonds. It doesn't have to be the pure, complete covalent system, and it definitely does not have to be a pure coordinate covalent system via organic synthesis or inorganic synthesis. Okay? All right, now, talking about the remediation, so we have to have a way of exchanging molecules. So there again, we're going to compare back to the basic clay, a natural clay that we've seen before. So as you can identify, right in the center of the clay picture, you can see the kind of the red, green, red, and purple spheres. Again, that's the aluminum silicates, right? The basic composition of our clay. And in between, you can see that there is the molecules of water as well as other natural ions that can reside inside of these layers. Now, a clay will simply only have what's called an ion transport or molecular transport occurring, because we're simply just talking about a molecule going in, just kind of hanging out, or an ion going inside. There's really no other chemistry that's going on. Simply go in, come on out. Now, another side, what could happen is what is called intercalation. Right? Intercalation is just a fancy word for, again, a molecule going inside of our framework, but is going to have a coordinating effect, which means it's going to bind to the actual metal. Okay, what's lesser viewed into this picture, if I can stretch it without too much, but as you can see at the very bottom, on the axial portion of our molecule, of our metal framework, we have two water molecules that is coordinated to this metal center. Okay, so the idea behind the intercalation is, well, maybe we can get a molecule that can go inside and displace the water molecule and have a coordination to the metal center. Right, so where one side would be simply a more weaker interaction, molecules can go in, hang out, come back out if it wanted to. The other side would be almost a more permanent effect, where we would actually coordinate a some other molecule in replace of water. Okay, what's the big difference? Okay, well, if you commonly just think of boiling point of water, 100 degrees Celsius. Okay. In my little hydrogen bonded system, so that's another one for me over there, as you can see by Hogan. Okay. If we coordinate a water molecule like you can see in this framework, does this water molecule come off at 100 degrees Celsius? No. It's probably closer to about 160 to 180 degrees. So it becomes more stable inside of the framework as opposed to a free-floating molecule that can just come right out. Okay, so that gives us more stability. These frameworks have very high potential to take heat and keep its composition without deconstruction. It's going to be another key important factor into these types of frameworks. Okay? So why study these, right? Because that's pretty much what everybody wants to know. Why the heck are you going to study this? Well, money, of course, right? We want to do all this so we can get funding, get some nice grants. Okay, but why are we going to study it to get money? How? Right? Some of the few basic ideas behind these are sensors. Right? One of the key common ideas because again, they're metal, so you'll tend to see a lot of photoinduction, a lot of luminescence possibilities. Okay, one of them that I've seen without actually shining any type of light onto my framework is actually just into the idea of when it accepts a molecule, it puts a gas molecule, it actually changes color. Okay, because a lot of them what I use is going to be it's a zinc-based molecule. So right at you can see the little 6 coordinate species, right? Those are all zinc molecules, or zinc ions, sorry. Okay, well, once you coordinate these ligands onto the zinc, right? We all know zinc salts, pretty much they're white powders, right? You coordinate this molecule to our zinc, it actually turns orangish. Okay, once we put molecules inside of the framework, it actually turns to a brown crystalline substance. So we actually can visually tell, do we have a guest molecule inside? Is it porous, meaning nothing inside, or did we deconstruct everything and go right back to zinc? So we have a fantastic kind of a coloration to identify. Right? So storage, right? Everybody's heard of hydrogen storage and storage of ethanol and other types of gases and flammability things. Right? Same thing here. If we could put a molecule inside, say a hydrogen gas, right? If we could put hydrogen gas inside of our framework, right? Pure hydrogen gas, we all know that's a bad thing, right? If you have it into a container, right? Think of the Hindenburg. Okay, that's a classic example. Hydrogen-filled Zeppelin, kaboom. Okay, bad. Right? If we put hydrogen gas into our framework, I've seen these studies, I haven't tried them yet, but you can actually take a framework like such, fill it with hydrogen gas inside, and actually put it to an open fire, nothing. Okay? Ease of storage. We can reduce the flammability of certain compounds just by having them inside of the framework. Fantastic. Okay, separations, we will see later on, probably one of my last conclusions if I get to that point right now. I don't know if I get past the intro, but we'll see at some point, one of my next ideas with these is going into separations. Could we separate specific isomers inside of our framework? Okay, and then lastly, catalyst. Well, it's a metal. Heck, it's got to be able to do a catalyst at some point, right? So, all right, so without further ado, we're going to try to get into this. So how are we going to investigate these materials? So what we're trying to talk about is what type of techniques can we use? So bringing in my second background of an instrumental analysis person, we're talking about the fancy instruments. Okay, so as you can see, a nice large list. Number one is X-ray crystallography. Okay, my second trait after behind a standard inorganic chemist, analytical chemist. All right, I'll also do X-ray crystallography. Right, we get bored, you got to take on something else, right? So look into what's called single crystal X-ray diffraction, where we grow very nice single crystals, shine X-rays on it, look at its diffraction patterns, and identify and conclude what type of atoms do we have. And we can generate what's called its unit cell. I'll leave that shortly. Okay, if you ask them what is a unit cell, just wait on. Just give me a minute. Okay, and also we can take and look at what's called powder X-ray diffraction, where if we can't generate a nice single crystal, because growing single crystals are a very tedious and difficult task, well, as long as our material is slightly crystalline, we can actually run a powder diffraction on it. Get similar results enough that we can go back and relate it to that unit cell and determine, well, hey, do we have our framework or not? Okay? And everything else is going to be common, NMR, basic IR spectroscopy, but the next big one is the thermal analysis, because remember I was telling you about that thermal stability. Okay, so what we'll look at is using what's called a TGA, a thermogravimetric analyzer, and differential scanning calorimetry, DSC. Okay, and I'll tell you a little bit more about these in a wee bit. And lastly, good old chromatography, right? Specifically a GCMS, so that if we have molecules inside, we should be able to separate them and identify specifically by using the mass spectrometer exactly what's inside of our framework. So it gives us all this insight. All right, so basically, I'll kind of go through this quickly, right? If you remember unit cell, again, back from Gen Chem 1 days, it's our repeating pattern of our molecules, because everything we're going to be talking about is in 3D, right? So if we get a unit cell to be three-dimensional, that unit cell is going to repeat in X, Y, and Z. So it's a reoccurring kind of cell dimensions that we can use to our advantage. So what we classify on our planar set is going to be the A and B axis. The C is going to be the distance between our layers. Okay? And for thermal analysis, so this is again a rough cartoon of the basic idea. So a thermal analysis, or TGA, is simply, it's a very sophisticated furnace with a microanalytical balance. So we're heating up a sample and we're measuring its mass at the exact same time. So what we can identify is once we start off in the very beginning, we have our 100% mass of whatever we have. Say we have two guest molecules. We increase temperature, we will see a nice little drop off for a guest molecule. All right, so we will see a loss of mass. And we would have one left. So again, if we keep on heating, we would see another loss associated with the other guest molecule, leaving us with just the basic host, which then can either undergo a vaporization or decomposition depending on what type of molecule we have. Okay? Everybody's got that? Make sure we have a short test after this. No. I got plenty to grade at home, so I don't need any more. All right, so one of our biggest research questions, so now we're going to move into research. Okay, our biggest question we have is kind of what I was mentioning earlier. Can we control the synthesis of layered frameworks just by using hydrogen bonding only? So you probably already have an idea what's the answer. Okay, but I like to show you guys not everything is cracked up what it should be or what it's supposed to be. You know, not every time we go to the lab, things work. Right? If anybody's already doing undergrad research, you know that. You probably had some good days and some bad days. Probably more bad days than good days. I'm the same way. Okay, so kind of correlating this kind of back to where we started, right, from basic organics. So here we have just a, you can see an orthohydroxybenzoic acid plus what's called benzylamine. So my main synthon, all right, my synthesis of my hydrogen bonding as the synthon, okay, what I'm going to be using is what's called the ammonium carboxylate. All right, so I'm actually going to take hydrogen bonding to a second extreme and undergo what's called charge-assisted hydrogen bonding. Right, because if inorganic cation anion is very strong, hydrogen bonding very weak, well, what if I combine the two? Use a little of electrostatics plus hydrogen bonding. Hey, it makes sense. Increases stability. Okay, so as you can see, if we take our two components, allow them to crystallize, mix them together, allow it to crystallize, we generate this lovely crystal structure. So anytime you see a picture like such in my slide, that's actually from an X-ray crystallography single crystal structure. Looks pretty, right? Does it look like anything happened?
It looks like the hydroxide and the carbonyl things swap.
Just different orientation, but actually nothing happened. Because if you can see at the top, there's our carbonyl at the top, so still at the top position. And to the left, I'm sorry, to the right, there's our hydroxyl group. Nothing happened. Right, there's that idea that, you know, not everything works perfectly. Okay, no crystallization. We only crystallize the starting material. All right, so probably you're looking at it, well, we have to start thinking, well, why? Right, something doesn't work, why? Right, one of the biggest ideas we can just quickly think of is got to be steric hindrance, right? You have a carboxylic acid group right neighboring to a hydroxyl group. There has to be some sort of sterics, highly possible electronics as well, but the sterics is probably what's going to drive it the most, and so therefore, too close in proximity, not enough ability for the amine molecule to go in and undergo the deprotonation and protonation of the amine. So nothing happens. Okay, so well, let's get rid of the steric hindrance, right? So if we had an ortho substituted group, well, what can we do to alleviate that hindrance? Let's go para, right? Just put it as far away as possible. Okay, so there we go, doing the exact same thing, para-hydroxybenzoic acid plus benzylamine, allow it to crystallize, and look what we have. So hopefully you can identify the little bitty white spheres are the hydrogen, so look at the top. Do we have our hydrogen anymore? No. So we had the deprotonation of our benzoic acids. And look at its neighbor. We now have a nitrogen that has, you can't see the third hydrogen, but it's pointing right back behind that planar bond. So we had the ammonium. We generated a salt, yes. All right, only I can get that excited over a salt. Okay, because remember, This is just the unit cell. This is the one block. So, do we have a layered framework? Well, what we have to do is, well, we need to put together our repeating unit cells and identify, is it a layered framework? Well, somewhat, right? You can see it's got this little bending pattern, nice little 1D ribbon pattern. Hydrogen bonds, yes, are present. You can see them in between. But, grand scheme of things, can we put something inside of that? More than likely not. I forget the calculated void space, but it's probably less than 5% of total volume. It's going to be hard to squeeze anything there with 5%. Okay? So think again about your house. If you had 5% of your total living space, 5% is available. Can you give that to somebody else to live in? I know I don't want to live in that. I'm a big man. I need 6%. Okay? Maybe not 6%. Okay, so, but the idea is we generated the hydrogen bonded framework. It's not ideal. It's not what we're truly looking for. Because again, we want to have what's called a lamellar hydrogen bonded framework. So we want it nice and flat sheet-like. Right? But we're not there. Okay? So here is what's called, this is powder X-ray diffraction. So this is the second method that we can use to help identify, do we have a framework or not? So on the left side, you again have the para-hydroxybenzoic acid, and on the right is from the hydrogen bonded framework that we just showed you. All right, everybody sees that one nice clear difference, right? Right there, somewhere between 7 and 12. Well, what the heck is 7 and 12? Well, it's 2 theta, okay, based on our axis of our X-ray diffractometer. All right, and the Y is basically intensity, how much of it's there. So you can see the most intense peak from our framework is right there in between 7 and 12. And do we see anything between 7 and 12 on just the molecule? No. Okay, again, because a basic molecule is wee big, give or take. And when we actually expand it with hydrogen bonds and generate the layered framework, it becomes larger. So again, we're measuring that distance between the layers. So, basic molecules will have very small interlayer distances. Okay, but frameworks will not. All right, so this is why we can use X-ray diffraction, powder diffraction very quickly. We can generate these types of patterns by about a half an hour. Okay, to generate these lovely single crystal structures, probably talking about easily, since I don't have a diffractometer, I have to ship it off to College Station, so there's a couple days in transit. He gets my sample, places it on, runs data overnight, and then eventually I get it back, so we're talking about easy 5 days. Okay, quick. All right, so again, another little quick framework just to show you. So now we're going to use cyclohexylamine. So now we just went and removed pretty much all of the aromaticity out of this molecule using its alkyl version. All right, so we expect something similar, right? We can see from already from our unit structure, our unit cell, we have the carboxylate, so we know we have the salt. Yes, we love salts. All right, so again, same thing. Do we have a layered framework? Yes. Is it better than the previous one? What do you think? Remember the key word, lamellar. Flat sheet-like. Is this better than the previous?
A little bit better.
Yeah, a little bit better. It's not as jagged, right? It's probably almost, I think when I measured, it's about a 65-degree angle, give or take, maybe 70-ish. All right, here, we've reduced that difference, so we're almost getting kind of flat-like, right? So we're getting closer, okay? But can we stick something inside? What do you think? Can we squeeze another molecule in there? Can we get another person to fit right in between these two people? Yeah, there's the handle of the chair, right? Would be comfortable, but in this case with molecules it won't happen. Okay, so the answer is no. So, looks good, promising, but alas, molecules can't go inside. Okay, and then just again, repeat one more time. Now again, you can see another ortho-substituted amine, and alas, what did we generate again? It's just the starting material. So we're seeing the correlation back again, that it is a sterically driven crystallization or acid-base reaction. So the ortho-substituted molecule or amine doesn't work. Okay. So now just some special thanks, because this was all preceded also with other molecules from my previous institution before I moved to Texas A&M Texarkana. I actually had students who worked on the phthalic acid series. So looking at terephthalic acid, isophthalic acid, and actual phthalic acid, did the exact same correlation. Guess which one worked the best? What do you think? Terephthalic acid. Again, because of that one form. We did not generate not one quality crystal structure framework from phthalic acids. It was all just pure phthalic acid each time. No surprise of what we've seen, right? Even bulkier. Okay? And now again, just another repeat back to that athletics thing. The gentleman who actually did the phthalic acid series, Shane McClendon, was actually a starting cornerback on our football team at Northwestern State. So NSU in Natchitoches, Louisiana. He was actually a football player. So there's that idea, you know, athletes can make damn, oh, sorry, I don't know if I can say that, but dang good scientists. Okay? Okay, so now looking into going into the inorganic side. So want to dive into that kind of what I like to classify, because everybody likes to come up with acronyms nowadays, right? Everybody's heard of the MOF, M-O-F, right? That's a metal organic framework, right? Widely studied, many, many years. I don't know what textbook do y'all use for Gen Chem. Do y'all use the Burston and Brown?
We use Tro.
Okay. Well, the reason why I say Burston and Brown, again, is the cover of the last two editions are actually, they use MOFs on their cover. That's why it's been a perfect plug for the research in the textbook. Okay? So, I have my acronym, what I call an HMOF, right? Same thing, kind of hydrogen bonded metal organic framework. Okay, so again, the whole idea behind this is simply, it's the approach. Okay, we can generate simple, stable frameworks that is benchtop chemistry friendly. Okay, a lot of MOFs that, one of the biggest guys, his name is Omar Yagi out of UCLA. Well, everything has to be done under inert gas and inside of the little glove hands, or the little glove boxes. Anybody worked in those? They're not fun. Okay. So a lot of those reactions have to be air sensitive. Well, I can make this right on a benchtop, and I do with undergraduate students. So very simple, very easy. It's so easy, an athlete can do it, I'm joking. I'll put myself. All right, but it's simple. All right, as you can see, I don't have the full synthesis of it, but to make that nickel complex at the top, I switch between nickel and zinc a lot. They have similar properties. Right? Take a nickel salt, nickel sulfate, nickel chloride, doesn't matter what it is. Put it in water. Take the chelating ligand, that's the pyridine 2,4-dicarboxylic acids, pretty much in a methanol water mixture. Let it dissolve, put the two together, and they precipitate out. Comes out nice collection. I could take just a basic filter paper and do basic gravimetric filtration. Simple. Okay, simple, simple, simple. And then once I'm ready to make frameworks, I just simply take that powder, in this case this nickel one, nice beautiful blue powder, baby blue powder. That's one other good thing with inorganics. We get the lovely colors. Okay, anybody's been in an organic lab? So what colors do y'all get? A lot of white, yellow.
Wow.
Yeah, it's a black if you overheat it. But, you know, and no offense to any organic chemists, it's plain. So that's why the love of the metal ions, we generate all of these lovely colors. Okay? So, take our metal complex, hit it with some sort of an amine, and again, the synthesis to form these, especially here in these closed packed systems, okay, because all we take is that metal complex, it doesn't dissolve in water, so we kind of suspend it, and we can just simply just add drop-wise with the amine, and what happens, it just mixes, stirs, and it goes completely in solution. So once we have the acid-base interaction to generate technically another large version of the salt, it goes right into solution. Beautiful. So again, we know that we have the ionic system to generate our layered framework. So simple, ease of control. Okay, so I forgot I put the slide in. So there's actually the synthesis right there what I was mentioning with respect to the zinc compound. Exactly the same. Zinc sulfate plus the pyridine dicarboxylic acid. And we could again get a lovely crystal structure showing that we do have the 6-coordinate zinc compound. Great. Right. And again, same thing what we were talking about, taking that metal compound and adding our amine. And I have to admit, I stole my slides and trying to be quick. The conditions that are needed is not the methanol water DMF, okay? Because it's just a monoamine, we really just need methanol water. It goes right into solution very easily, okay? And again, you can see the crystal structure showing the deprotonation of our carboxylic acid. It's giving us the dicarboxylate. So we've now deprotonated on both ends of our molecule. And as you can see, again, just to show you based on my crystallographer, why I love both of them to death. Because actually, once they got the data, this is actually what was sent to me at first. And I told him, I said, what the heck is that? Because that's your counter ion. I said, no, please, no. So, well, we got to think what happens is, remember, molecules have all those degrees of motion, degrees of freedom. So this counter ion is doing this inside of that crystal structure. It's moving. So what you're seeing is all the different orientations that could possibly happen. Fantastic. So, thank God for mathematics, a lot of modeling. He can go in and give me a nice clean version. As you can see, a model, so one specific, just setting all parameters to give me one of my counter ion, where I can generate the lovely picture that actually looks like a cyclohexylamine. And voila, there's that 3D framework. Very pretty, very nice, very ordered. Okay, but again, let's go back to previous. We have the nice lamellar functionality, right? It's nice and planar, very sheet-like. All right, do we think, can we squeeze molecules inside of this? We may, if the right molecule exists. Space-wise, it's actually very small. Okay, it looks like there may be some room to squeeze inside between the two cycloammoniums, but I haven't seen anything. I've tried some of the smallest, easiest solvents to crystallize, which is acetone. I just can't get it to stay. Unless, by the time I submit my crystal structures, that the acetone's coming out of the framework, which is a high possibility. So that's why all those other techniques, those fancy instruments, come in handy. Okay? All right, so same thing. What can we do? How can we identify all this? So the two biggest things that we like to look into is the use of TGA and XRD. So again, we will know if we put something inside of our framework by heating it up, we will see a mass loss. And with XRD, we will see an expansion of our layer. Okay? If we put something inside, it should swell like our clay molecule, right? Well, that's the thought. All right, so real quickly, I know we're going to try to wrap it up shortly. We're getting close to that time. I can go for another 2 hours if you want me to. I'd love it. So we're going to look at intercalation experiments. So this type we're looking at is more or less the molecular transport, because you can identify these are all just basic little molecules, nothing too heavy on the coordination site. Okay, so we would expect just to put these molecules inside of the framework, and will it stay? Okay? Alrighty, let's see what happens. Alright, so here's a picture of a TGA with all of those different choices that we went ahead, and what you can identify is, except for that one little outlier, the pink one, the rest of them, do they look quite similar? Yeah, they do, unfortunately. And when I do my calculations, it shows that the only thing I'm losing is coordinated water. Okay, because of once we heat it up high enough, which means there's no molecules inside. Okay. And we again could prove it again by overlapping all the different powder XRDs, the powder X-ray diffractions, where we're looking for specifically the three components of the unit cell, the A, B, and C. So by looking at what are called the Miller indices, so our C parameter is at 0, 0, 1, the distance between our layers. All right, you can see technically there is a very, very small shift to lower 2 theta. How small of a shift? I think it's probably measured about 0.2 angstroms. I think that would make a molecule move with 0.2 angstroms difference? No. Okay. So data showing us nothing's going inside of this framework, nothing that we could put in for a non-coordinating system. Okay, it's bad. Well, what about coordinating, right? What if we actually do the intercalation where we exchange? So now we can bring in all these pyridines, because that's one of the best molecules if we want to coordinate to a metal center. We all know pyridine has those lone pair of electrons that's pointing out from its cyclic ring, right? Great for donation into a metal center. So we went ahead, and why not? Let's try all these different pyridine-based molecules. All right. Looks different than before? If you're, yeah, a lot different. Okay. So good news is, again, like we've seen before, visible color change. Once we put those the pyridine molecules onto the metal center, where it used to be that nice baby blue powder, it actually turns very deep purple. Okay? Very consistent color change. So we're having to get a nice little electronic difference that's going on side of our metal, or on the actual metal center, seeing, again, a nice color change, and then we're seeing a very evident TGA weight loss. All right, and now we can go to, again, back to the powder. Back to powder XRD. Last time, right on that 001 Miller indice, we saw it was just perfectly straight down. Well, look what you see now. There's definitely 2 of them that's well past 2 theta of where we began. Somewhere's near 7, actually it's like 6.9, angstroms, and now we're closer to 5. So if we had an interlayered distance of about 13.5 angstroms, we now are showing 2 molecules that are inside that has swelled our interlayer distance, and now we're pushing closer to 16 angstroms. So now we're seeing an easily 3 angstrom difference. So here we're probably, with the coordination, it's going to be more difficult to identify a greater swelling of our lattice. Why? Because now remember, we're simply replacing that water molecule. So it's not going inside and freely floating. So there's already some distance that we already have to take into consideration that we're going to lose. So, seeing very good data. All right? Now, so kind of a summary from all of this. All right, can we have a reliable synthesis? Yes. We've seen it. We can make these metal inorganic frameworks very easily, very simply. Can we undergo a coordinative intercalation? Can we exchange water molecules for something else? The answer is yes. Can we undergo a small molecule, the non-coordinating intercalation? With this, no. Okay. So what that tells us, our molecule has to have a more porous nature. Okay, I'm not getting close at a time. I'll just do a recap of something else real quickly. So in order to make pillared and porous frameworks, we're just going to change our synthesis by a little bit. Where we had a monoamine, we'll put a diamine because now we want to tether both ends of our frameworks together. Okay, so, little cartoon, and so some diamines, and so voila, there you go. There's one of them. So as you can see, the diamine is has the interaction with two neighboring layers, giving us a nice pillared structure. Okay? And we could put molecules, because there was actually one there when we crystallized it. Hey, little old acetone. He found himself a nice home. Okay? So, quick synopsis. Well, let me just mention this. So what's very lovely about these types of pillars, pillared frameworks, as you can see, it has a nice one-dimensional channel right through. But if we take that framework and just turn it 90 degrees that we're looking at its side, well, we have a nice wall. So nothing actually can escape. There's only one way in, one way out. Okay? Alright, so I did the exact same thing. I'll just do the quick synopsis. I did the same thing. Non-coordinating molecules, a variety of them. Some TGAs again. There's the data. Okay, then we can identify theoretical what should be in and what if we did put it and what happens with our TGA. Okay. Powder XRD, everything all the same. So what I want to show you is again, this is what we used. Okay, those are the ones that actually went in that pillared framework. So for a non-coordinating system, we actually put free-floating molecules. So this is what allows for the remediation. We can actually separate and remove molecules and put them inside of our framework just by using this little pillared guy. Okay, so I'm just going to go ahead and move all the way to the end and say, there's my conclusions. All right, we already recapped, so I'm just going to say thanks. One of my biggest students, he just moved back to Russia. He finished up, he's in medical school in Russia, Peter Igor. My two crystallographers, Joe Rabinsky's and Frank Franzak, both one from A&M and the other from good old LSU. So sorry, remember I am from Louisiana. And then again, thanks for my institution, TAMUT, the CASE, so that's the College of Arts, Science, and Education. We just converted to that. So thanks for all the chemicals lab space, and thank you for your attention. I appreciate coming and letting me talk to you about these guys, and hope you enjoy the rest of your day.